We will continue on in what we were doing last time. Actually, let me do this. So we're kind of doing sections 5.2 and 5.3 together. Because they're so closely related. And that was trig functions with unit circle. Okay. And the last thing that I was writing on the board we figured out that, well, we know how to calculate, or we know where sine of theta and cosine of theta come from. In terms of the unit circle. So we know sine of theta and cosine of theta and how they relate to the unit circle. And then last time we said, well, now that we can calculate sine and cosine, we can either calculate that manually based on the unit circle, or we can use our calculators. Then we can say, well, every time I want to find a secant of theta, I can take 1 divided by cosine of theta. Every time I wanted to find cosecant of theta, I can do 1 divided by sine of theta. If I want to do tangent of theta, well, that is on the calculator. Or I should say, and also, tangent of theta could have also been found by taking sine of theta divided by cosine of theta. Right? And then the other trig function we dealt with was our cotangent. And our cotangent of theta, you could have either said, well, it's actually cosine divided by sine, cosine of theta divided by sine of theta. Or, since that's the reciprocal of this, you could have said it's the reciprocal of tangent. Today I'm not going to write this, but I wrote this last time. These all work so long as denominators are not 0, right? We can't have denominators 0. If denominators are 0, then those things don't exist. So that's what we did last time. That was kind of what we ended on. So let's once again use those identities. That's what they basically are. These are trig identities. We'll see a lot more trig identities in chapter 7. But we'll use those trig identities to calculate certain things. So let's calculate secant of 3 pi over 7. And calculate, let's say, tangent of 4 pi. And then let's do cotangent of 8 pi over 3. By the way, most of the times where I put radians, I throw in the symbol pi, but you could have also had something, let's say we did cosecant of just 3.82. Right? Doesn't always have to be that. Doesn't always have to include a pi symbol is what I'm trying to get at. So let's go ahead and calculate those. I know we did some of these calculations or something similar, different numbers last time, but gets us in the right idea. In fact, why don't you try these on your own just for a second, using these identities. Okay. All right. So if you get used to these, using these identities, it goes pretty quick. Okay. So that first one, secant, what I type into the calculator is 1 over cosine of 3 pi over 7. And when you do that, you get about 4.49. I'm going to come back to the tangent one in just a minute, okay? I'm going to do the other two first. Tangent is something we can type into our calculator, but something funny happens in 4 pi, so that's why I want to put it on. All right, cotangent. Now, you could either have typed in cosine of 8 pi over 3 divided by sine of 8 pi over 3, or what I typed in on my calculator is 1 divided by tangent of 8 pi over 3. Either way, on that,
Connected it.
fine.
Okay.
Oh, somebody's telling me. Right here. It's muted. Weird. Huh. Yes, they muted themselves. So you got negative 0.58. Okay. Cosecant of 3.82 is 1 over the sine of 3.82, which again, I should say, keep using equal signs, but technically it should be approximately. I got negative 1.59 approximately. Now, tangent of 4 pi is kind of interesting because if I type that in on my calculator, I don't know what your calculator gave you, but mine gave me a scientific notation of negative 2 times 10 to the negative 13th power. Okay. That's a very, very, very small number in absolute value. That's basically almost 0. In fact, if you round this to 4 decimal places, you get a 0. It turns out that technically it should be 0. Think about that unit circle and what 4 pi is. Well, 2 pi goes all the way around once and gets you to this point. Another 2 pi, that'd be 4 pi, go all the way around again and get you to this point. So we should be at the point 1, 0. That means technically what we should be doing, right, it should be the fraction 0 over 1, so it should be 0, right? It should be 0. But my calculator, the way it works with tangent, it didn't give me exactly 0. It gave me something very, very close to 0, but it didn't give me 0. And this is kind of one of the intricacies of the calculator, all right? That when it's calculating some of these things, it might not give you an answer that's perfect. It might be off by just a little bit. That really doesn't affect things like if our answer is 4.49, because if that answer is off by, let's say, the 13th decimal place, well, that's never going to show up in our, as an error here. If this answer was off by the 13th decimal place, we're not going to get any different things. We're not even going to see a difference on our calculator. But with things like 0, sometimes you get these weird scientific notation errors, right? So hopefully you recognize when you get that scientific notation that what that really is doing is that's a slight calculation error on the calculator, which should be in fact 0. Does that make sense? By the way, if you do one more, let's say we type in tangent of 3 pi. Actually, no, I don't want to do that. I want to do tangent, let's just do tangent of pi over 2. That'll be easier. you should end up with a domain error. All right? You should end up with a domain error because pi over 2, we're at the point up here, 0, 1 on the unit circle. And so fraction-wise, sine over cosine, we're dividing by 0 there. Okay? So if you happen to have a denominator of 0 in any of these things, then on your calculator, it's going to show up as a domain error. Right? For the homework, if you ever run across that, just type in capital D and E for does not exist. All right? So that's what dividing by 0 looks like. On your calculator, if you type something in and it causes you to divide by 0, it's going to give you a domain error. And you just write, that means tangent of pi over 2 doesn't exist. Now, the other thing we can do, based on these relationships, is if I said that sine of some angle, I'll call this angle A, capital A. If sine of some angle A is 0.75 and cosine of that angle is some other number. Let me figure out what that would be. Let's say it's 0.66 roughly. I'm just trying to get two numbers that work out. That's all. So let's say we have this sine and this cosine. Okay. Let's find secant of that angle. And let's find cosecant of that angle. And let's find cotangent of that angle. And let's find tangent of that angle. So if we know sine and cosine, then we can find all the other trig functions, the outputs of all the other trig functions. Okay. Secant is 1 over cosine. So that's simply 1 over 0.66, whatever that happens to be. I'm just typing that in on my calculator. I get about 1.52. Cosecant is 1 over sine. So that's 1 over 0.75. which gives me about 1.33. Cotangent. Well, what I would do is I would use this version of cotangent since I have cosine and sine, right? So it's gonna be cosine of the angle divided by sine of the angle, which in my case is 0.66 over 0.75. I got about 0.88. I got exactly 0.88. And then tangent, well, I'm gonna use this version of tangent, the sine over cosine version of tangent. So tangent is always sine of the angle divided by cosine of the angle. So that's 0.75 over 0.66. Which is about 1.14. That's pretty straightforward. Now, if you have sine and cosine, we can make these other ones work. But it turns out, if I have almost any two others, there is one exception. You don't want tangent and cotangent. But if you have, for instance, sine and secant, you can make it work. If you have sine and tangent, you can make it work. If you have cosine and tangent, you can make it work. You can't have sine and cosecant. You can't have cosine and secant. But a lot of other combinations of knowing 2 out of the 6 trig functions can generate your other 4. Does that make sense? So a lot of times, here we had sine and cosine, and we can generate our other 4 trig functions. But I can do that same thing with other versions, other combinations. So let me give you an example. Let's say I know tangent of an angle, I'll call the angle B, capital B, is equal to 2.01. And I know that cosine of angle B is negative 0.45. Let's find the other 4 trig functions, or the values for the other 4 trig functions at angle B. So I want to know what the sine of B is. I want to be able to find the secant of B. I want to be able to find the cosecant of B. And I want to be able to find the cotangent of B. I already have tangent and cosine, so I don't need to find those two. But I want to find the other four. Everybody get what I'm saying here? So we have two trig functions. We need to find the other four. And there's a lot of combinations that can make this work. Now, some of these are easier than others. So let's deal with the ones that are going to be easiest. Cotangent's going to be really easy this time, because I can use the fact that the cotangent is just 1 over tangent. So I use the cotangent is 1 over tangent of angle B. Since tangent of B is 2.01, that means cotangent is 1 divided by 2.01. That's about 0.50 rounded to 2 decimal places. 0.4975 if you go off one. Another easy one is the secant, because that's an easy relationship with cosine, right? Secant is 1 over cosine . So 1 over negative 0.45. Gives you a negative 2.22. Lots of twos there. So that was pretty straightforward too. Now, these other two, the sine and the cosecant. And cosecant is just 1 over sine. So let's focus on the sine for this case. I have a tangent and a cotangent. So how do I find sine if I'm having a tangent, or not, I say cotangent, I'm sorry. I have a tangent and a cosine, excuse me. And I need to find sine. So here's what we're going to do. We're going to use this identity, that the fact that the tangent is sine divided by cosine. So we're going to use tangent of an angle B is sine of B over cosine of B. Notice that if I plug in my value for tangent as 2.01, and I plug in my value for cosine as negative 0.45, I get 2.01 is equal to sine of B divided by negative 0.45. Multiplying both sides by negative 0.45 gives me that well, let me rewrite this. I'll write it where sine is on the left. Sine of B is going to be 2.01 multiplied times negative 0.45. based on that. I got negative 0.90 rounded to 2 decimal places. Negative 0.9045 if I go out more. Does that work? So it does take a little bit extra computation, but what we do is we go down to this, and if I know 2 of these, I can find the third. So I go to this identity. Tangent is sine over cosine. If you know 2 of those, you can find the third. Doesn't matter which one. Same thing with cotangent. Cotangent is cosine over sine. So if you know 2 of those, you can know the third. And then what I would do for cosecant, now that I've found sine, I just take cosecant as 1 over sine of my angle. And if you round to 2 decimal places, it's probably not going to hurt too much. If you want to go all the way out to 4 at this stage, that's fine. Negative 0.9045. If you go 1 divided by negative 0.9, you get negative 1.11. If you do 1 divided by negative 0.9045, you get negative 1.11. So it's the same thing either way. For this one, sometimes it might be off by just a little bit, but in this case, they both round to negative 1.11, whether you use the exact value here or whether you use the rounded value. Does that work? And again, by the way, a lot of the combinations where you're given 2 trig functions, you can come up with the other 4. Okay? If you have sine and cosine, then obviously you can come up with the other 4. If you have tangent and sine, you can come up with the other 4. If you have tangent and cosine, you can come up with the other 4. If you have cotangent and cosine, or cotangent and sine, you can come up with the other 4. If you have secant and cotangent, or cosecant and cotangent, you can come up with the other 4. If you have secant, you can find cosine, and then you guys get the idea. There are a couple of them that you can't do it with. If I just have a cotangent and a tangent, that doesn't work because they're reciprocals of each other. If I just have a cosine and a secant, that doesn't work because they're reciprocals of each other. And sine and cosecant, that doesn't work either. I can't find the other 4 because they're reciprocals of each other. So the ones that are reciprocals of each other, if you get those 2, you can't come up with the other 4. But if you have any 2, you can come up with the other 4 as long as the 2 you're given aren't reciprocals of each other. All right. Any questions about that? Good. Well, that is 5.3, and we are going to use those identities throughout these next few chapters, especially in chapter 7. We'll use this kind of logic a lot, that tangent can be written as sine over cosine, and secant is 1 over cosine, all of those identities. So those are going to come up in a lot of other places as well. Okay. All right. Let's move on to section 5.4. Section 5.4 is about how trig functions relate to right triangles. So trig functions and right triangles. It turns out that if we have a right triangle, and I'm going to draw it this way, where the right angle is on the lower right hand side. Right, so that's the 90-degree angle. And I look at this angle here. This angle here we'll call theta, just like we use theta for a lot of our angles. So the three sides of the right triangle, the ones that form the right angle are called the legs, and then the one opposite the right angle is called the hypotenuse. Right? So this is the hypotenuse. And generally speaking, when we're talking about trig functions with right triangles, we call this leg the leg that is opposite of our angle theta. So it's the opposite, and by opposite, I mean opposite of angle theta. This leg is the leg that's adjacent to angle theta. So we have the opposite side, the adjacent side, and the hypotenuse. The opposite leg, the adjacent leg, and the hypotenuse. It turns out that we can say, if we try to calculate sine of theta. Now we know how to calculate sine of theta. It's the wrapping function on the unit circle, and we take the y value, right? Well, the sine of theta on a right triangle can be calculated by just dividing the opposite side by the hypotenuse. And by that, I mean the lengths. The length of the opposite side divided by the hypotenuse. That's the ratio. The cosine of theta is the adjacent side divided by the hypotenuse. The tangent is equal to the opposite side divided by the adjacent side. By the way, I could have figured out what the tangent is by just saying, well, isn't the tangent sine over cosine? And if I could take this one divided by this one, the hypotenuses cancel each other out, and you're just left with opposite over adjacent. Does that make sense? So you could have done that as well. And then if you want to find the other three trig functions, sine is related to cosecant. And remember, sine and cosecant are reciprocals, so you just flip the fraction. Hypotenuse, I'm not gonna write the entire word, just write height over op. Does that work? Hypotenuse over opposite. Cosine is the reciprocal of secant, so if you wanted to find secant, you would just take the reciprocal of your cosine. And tangent and cotangent are reciprocals as well. So I just take the reciprocal of tangent and you get cotangent. All right, we saw that a little bit earlier. Okay. Most people don't memorize these last three. The cosecant, secant, and cotangent, because they're just reciprocals of the other three. Okay. But these three relationships here, these are what people refer to as the SOHCAHTOA relationships. Have you guys heard that one? SOHCAHTOA. All right. SOHCAHTOA is just a mnemonic to remember that sine is equal to opposite over hypotenuse. That's the first three. Sine is opposite over hypotenuse. The CAH in SOHCAHTOA stands for the cosine is equal to the adjacent over the hypotenuse. And the TOA obviously is referring to the fact that the tangent is equal to opposite over the adjacent side. So that's the relationship we have, the sine, cosine, tangent relationships that we have with right triangles. All right. So knowing those things, we can come up with the sine of whatever that angle is, or the cosine of whatever that angle is, or the tangent of whatever that angle is, if we know these three lengths. So if you know those three lengths, we can figure out what the sine, cosine, and tangent are. And we can also figure out cosecant, secant, cotangent. And again, these are very popular when dealing with right triangles, these last three. So I won't be asking you those types of questions typically. Right. Let's do a couple of examples.
I have to scroll over.
So let's say we have a right triangle. And this angle here, which we'll call theta. All right. Now, when I draw a right triangle, don't assume that you can put a measuring stick on these. You know what I'm saying? So if you get a right triangle, just because this is 5 inches and this is 4 inches on a measuring stick or on a ruler, that doesn't necessarily mean it's the proper scale. So when I write these things in, let's say I know this side length is 6.5 units, whatever the units are, could be inches, meters. This side's length is 3.8. And this side's length is 7.53. So I have those. And again, when I draw a right triangle, these sides might not be to scale. In fact, in this case, they are not. If you put a ruler up here and you measure that distance and call it 6.5, this distance would not be a proper 3.8 to 6.5 ratio. Does that make sense? So be careful about that. Don't use the ruler to try to figure out some of these lengths. We're gonna find out the lengths later, but. So anyways, when I draw a triangle, it's not always to scale. So let's calculate the sine of theta, the cosine of theta, and the tangent of theta. In this case, sine is opposite over hypotenuse. My hypotenuse is the 7.53 number. And for theta, the opposite is 3.8, and the side adjacent is the 6.5. Right? So in this triangle for theta, the opposite is the 3.8 side, the adjacent is the 6.5 side. So sine, when it says opposite over hypotenuse, that's the 3.8 divided by 7.53. Whatever that comes out to be is the sine. I got about 0.50. The cosine being the adjacent over the hypotenuse. Well, in this case, the adjacent side has length 6.5. The hypotenuse has length 7.53. I get about 0.86. When you find the tangent, again, that's the TOA part, so T OA, tangent is opposite over adjacent. Opposite, once again, 3.8. Adjacent, once again, 6.5. I got about 0.59. Oh, I'm sorry. That rounds to 0.58, doesn't it? Sorry. About 0.58, excuse me. It's on the 6 there, not the 4. So I can solve and find those trig functions, at least the outputs, if I have the right triangle. Let's do another one. And let's draw the right triangle differently this time. So here's my right angle over there. And I'm gonna make up some numbers here real quick. So, all right, my hypotenuse is length 18.2. One side is length 12.2. The other side is length 13.5. And I'm gonna do something a little bit different. I'm gonna put my angle theta in the top left corner. Is that all right? And I want you to do the same thing. Find the sine of theta in this case. Find the cosine of theta. And then find the tangent of theta in this case. All right. So here's the deal. If theta is situated where it's at right now, the hypotenuse is still the angle across from the right angle. All right, so that 18.2 is still my hypotenuse. However, the adjacent versus the opposite side. The opposite side of theta is this 13.5. And the adjacent side to theta is the 12.2. Does that make sense? So the one that touches theta is the adjacent. Whichever way you draw it, it's the leg that touches theta, right? That forms one of the rays, forming theta. So when we say sine is opposite over hypotenuse, then we're going to take 13.5 divided by 18.2, whatever that is. I'm just going to leave it right now. Did I? Oh, I already did that. Yeah, I might as well write it. About 0.74. Cosine of theta is adjacent over hypotenuse, so it's 12.2 over 18.2, and that's about 0.67. Tangent of theta is opposite over adjacent. Again, SOHCAHTOA, right? SOHCAHTOA. SOHCAHTOA. That's going to be 13.5 over 12.2. That's about 1.11. So wherever you put the theta, you can figure out the opposite adjacent. All right, so it's pretty straightforward calculations. Very good with those. Most people have not too hard of a time with SOHCAHTOA. Okay. Now, I do want to, before I move on, give you the connection between SOHCAHTOA and the unit circle stuff that we dealt with before. Okay. Now, this is not going to be on a test or on a homework or anything, but I do want to make some connections. Okay, so SOHCAHTOA and the unit circle. So let's say I have a triangle that looks like this. Okay. So I have a triangle, looks something like that. We have a right triangle here. And I'm going to put angle theta I'm going to put the vertex of angle theta. Let me say that again. I'm going to put the vertex of angle theta at at the origin. So I'm going to draw a grid, the rectangular coordinate system. I'll do this with green rather than. Now, here's what I do. I then look at the hypotenuse. Whatever the length of the hypotenuse is, I draw a circle of that radius. So I'm going to draw a circle with radius being the hypotenuse. If I was smart, I would have made a measuring stick. Can't do it now, can I? So. I'm going to draw that circle very well. That's not a very good circle, but you get the point. Okay. Notice while this is not the unit circle, it could be scaled down to the unit circle. So it could all be shrunk if I wanted to. So what this point is, this point here, it has some x value. Guess what the x value is? The x value is the length of the adjacent side, right? So the x value is the adjacent side. The y value is the length of the opposite side. Of that point. Okay. Now, let's say, for instance, the hypotenuse length is 7.53. Okay, just like this one. Okay. Then we'd be at the 0.65, 3.8. Did I get that? I'm not going to draw those numbers up here because I want to be clear about this. It turns out, if you drew a unit circle, smaller circle, well, the unit circle we know has this point, which is cosine theta, sine theta, right? How do I get out? Notice that that point is going to be right on the hypotenuse. How do I stretch that point out? Well, I stretch it by scaling it up. So this point here is actually also going to be related to cosine theta and sine theta, but it's going to be stretched out by whatever this radius is. All right. So now if I said, based on the unit circle, the unit circle says that sine theta is the y value on unit circle. Notice that on this circle, the SOH says that my sine value is the opposite of my value on the bigger circle. Basically saying opposite side over hypotenuse. The opposite side is whatever the radius is times sine theta. And the hypotenuse is the radius of the circle that I just drew. So all the SOHCAHTOA part, or I should say all the SO part is just saying, well, if we scaled this up by a factor of r, then the opposite side, the new y values are sine theta, and the radius is r. Instead of on a unit circle, the radius would be 1. And so we wouldn't see that r. If this should be a very obvious equation that sine of theta is the same thing as r sine theta divided by r, because the r's would cancel out here. On a unit circle, the radius is 1. So when we said sine is the y value on a unit circle, we were just using basically the SOH with r's being 1 in some sense. We didn't have to use the hypotenuse. We didn't have to use the radius of the circle. But you get that? And you can make the same connection with cosine. Cosine is the x value. And if I did opposite over hypotenuse for the sine, cosine would be adjacent over hypotenuse. It looked like r cosine theta over r. Right? So I'll write that real quick over here. Cosine theta equal adjacent over hypotenuse. That's r cosine theta over r. And then tangent of theta is equal to opposite over hypotenuse. What's the opposite? Well, that's the r sine theta divided by r times cosine theta. Did I say opposite or adjacent? I think I said hypotenuse, but opposite or adjacent for the tangent. And notice that's just sine over cosine because the r's are going to cancel out. Okay. So basically, these triangles all fit inside of a circle of radius which is equal to the hypotenuse. Okay, and because that happens, we get SOHCAHTOA. Right? That's the connection between circles and triangles. Right, these triangles can all be rearranged and written inside unit circle. Or not inside unit circle, inside a circle of radius r. And that's related to the unit circle by scaling up or down, whatever the radius is. That make sense? Okay, so that's the connection. That's not something that we're gonna focus. I mean, well, we need to understand that, especially when we get into later chapters. We'll talk about polar coordinates, and this will come back into play. But as far as like doing the homework, that connection is not super necessary for the homework. All right. Now, what we're going to do is beyond just calculating what the sine of the angle theta is, and what the cosine of the angle theta is, and what the tangent of angle theta is, what we're going to do is we're going to start solving right triangles. And I know I mentioned this, but I'm going to mention this again. SOHCAHTOA is specific to right triangles. If you have other triangles, it does not work. Okay? So when you're talking about SOHCAHTOA, that is specific to right triangles. Very important that it has to be a right triangle for this to work. And so we're going to solve right triangles, only right triangles here. So we want this. So this is still 5-4. We want to solve right triangles. So if we have a right triangle, what we have is 3 sides and 3 angles, right? We have 3 sides and 3 angles. So when we say solve right triangles, basically that means let me rewrite that. Solving means finding all of the sides and all of the angles. By finding all the sides, I mean finding the length of all the sides and finding the measurement of all the angles. Now, the nice thing about right triangles is we always know the measurement of one of the angles, right? The right angle is always 90 degrees. So that one's given to us. We know that one already. And then what we do is we label our right triangle. We don't want to use opposite and adjacent because the words opposite and adjacent are referring to a specific angle. So what we do is we label our hypotenuse C. I'm sure you've seen this before. We label our legs A and B. And then the right angle is obviously opposite to C. Opposite the hypotenuse. And we have to label these 2 other angles. Okay. Now, because we use theta in the SOHCAHTOA, and we've been using theta when we have one. I'm not gonna use theta anymore. I'm gonna use two other Greek letters. I'm gonna use the Greek letter alpha and the Greek letter beta. Beta kind of looks like a script B almost, and alpha kind of looks like, well, it's kind of like a fish there or something. Okay. But we're always going to have alpha is the angle opposite of leg A or side A. Beta is the angle opposite side B. That's for, so beta B, alpha A. This is the Greek alphabet. Alpha comes first, beta comes second. By the way, the right angle, we don't have to give a label to now, so generally we won't give a label to. I will ask you, hey, what's this angle measurement? Because we already know it's 90 degrees. But traditionally, the angle opposite of C is actually called gamma. And that symbol looks like that. It looks like almost an alpha rotating 90 degrees, but skinny. And obviously gamma is a 90-degree at right angle for all of the right triangles. So for us, gamma will be the right angle. So in all the right triangles, gamma is the right angle. So those are our labelings. And what we're going to do is we're going to solve a right triangle. And that means I'm going to give you a couple of these and we're going to find the others. Right? So if I give you A and C, we're going to be able to find the angles and B. If I give you A and B and beta, we're going to be able to find the other measurements and then also find the other angles. Okay. So finding to solve means I find all the sides and all the angles. Okay with that? Now the tools that I will use to solve the right triangles. One of the tools that I'm going to use is, in fact, SOHCAHTOA. All All right. And I'm just gonna write SOHCAHTOA there, and we know what that references to. So those three SOHCAHTOA relationships are gonna be helpful. If I know, let's say, the measurement of alpha, and I know C, that's the hypotenuse, then I can use SOHCAHTOA to find A and B. Did I get that? So I can use that relationship. If I know that's these two, a measurement and an angle, then I can use SOHCAHTOA to find the other measurements. So that's one thing we're going to use. Another thing that we're going to use is the fact that the angles of a triangle add up to 180 degrees. So if we're measuring our angles in degree, which is what we generally do with triangles, generally speaking, we measure the angles in degrees for triangles. But if we do, the angles have to add up to 180 degrees. I'm sure you guys have seen that before at some point in time. The third tool that we're going to use is the Pythagorean theorem. Which says that if I square A and then add it to the square of B, you have to get out the square of C. So A squared plus B squared equals C squared. And again, we have to force C to be the hypotenuse length here. You can't rearrange that. C has to be the hypotenuse length, A and B have to be the leg length in a right triangle. And again, I'm just going to note, both SOHCAHTOA and Pythagorean theorem only work in right triangles. Angles of a triangle adding to 180 degrees, that works in any triangle. But SOHCAHTOA, Pythagorean theorem only work in right triangles. So very exclusive to right triangles here. All right, so let me give you an example of how we are going to solve a right triangle. Let's assume I have this same picture. This, okay. So assume we have a picture. Alpha's over here, beta's over there, A, C, B, okay? Right. Okay. So we have that picture. Assume we have that picture, and we know that alpha alpha is 34 degrees and A is length 22.8. Okay. Right, following? So we know alpha is 34 degrees and the length of A is 22.8. Let's find all of the other sides and let's also find all of the other angles. Let's start with the angles. In this case, okay, it's not always the first thing I start with, but. All right, I know that gamma is 90 degrees because it's a right triangle. We always know in this section, that's always gonna be 90 degrees. In fact, you won't even be asked for that on the test or the homework. It'll just say, here we're dealing with right triangles, and it'll say, now what's A, what's alpha, what's B, what's beta, what's C. So, alpha, it says is 34 degrees. If I want to find my angle beta, since the three angles of a triangle have to add to 180 degrees, all I have to do is say alpha plus beta plus gamma add to 180. So 34 plus beta plus 90 have to be 180. And I can just take 180, subtract 90, subtract 34, and give me beta. In fact, on a right triangle, because gamma is always 90, the alpha and beta have to always add up to 90 degrees too. So you could have done that as well in a right triangle. So I just have to take 180 minus 90 and then minus 34. So I get that beta is 56 degrees. Okay. Now, here's how we can find the B and the C. Now, I always have to ask myself, what do I want to find first, the B or the C? Let's find the B first. Right? Is that okay? So let's find the B. Now we have to be a little bit clever. We're going to utilize the SOHCAHTOA. All right? Notice that the B and the hypotenuse are unknown. So the part of SOHCAHTOA that I'm going to use is one that does not include the hypotenuse. So I'm going to use the tangent part of SOHCAHTOA. Okay. And then I have to decide, well, which angle do I want to use? I think I will use angle alpha because that was the one I was originally given. It's usually a good move. So I'm going to use TOA with angle alpha. That is, the tangent of alpha is the opposite over adjacent. Now, I want you to understand what opposite is. For my angle alpha. For angle alpha, the opposite is the side length A. And for angle alpha, the adjacent is side length B. That makes sense? So for alpha, opposite is A, side opposite of alpha is A, and the side adjacent to alpha is B. Now here's the nice thing. I know A and I know alpha. So I can just take tangent of 34 degrees is equal to 22.8 divided by B. And then I can solve for B. Okay. I multiply both sides by B, I get B times tangent, and then I divide by tangent. I'm just going to rewrite this. 22.8 divided by tangent of 34 degrees. Whatever that is. Now be very careful on your calculator because so far you've been doing everything in how do I do this here? So far, we've been doing everything in radian mode, and then because we've been dealing with triangles the last 30 minutes to an hour, now we're using degrees. That's better. Okay, so make sure when you're dealing with degrees, your mode is in degree mode. Okay. And then, what was it? 22.8 divided by tangent of 34 degrees. And therefore, I know that my value of V is 33.80, roughly. Is that okay? So just make sure your calculator is in degree mode when you do that. With triangles, we're usually in degree mode. With unit circles, we're usually in radian mode. Okay, usually. All right, so I only have one more thing to find, and that's the C. Now, actually, with the C, I can find this in different ways. I have two options. One, I could use the SOHCA part, and in the kind of the same way I found B, my hypotenuse is the C, so I can use those. All right. Or now that I know A and B, I can use Pythagorean theorem to find the C. I'm going to do it both ways, and there's going to be a point to this. To show you both ways. So both ways for finding C. Okay. So here's what I'm going to use. Ooh, let me think about this. I'm going to use alpha again because that's the one I was given. So I'm going to use something of alpha. And I'll use A because usually I like using the given ones. Notice that this 33.80 was a rounded number. Okay. So I'm going to use, let's do opposite over hypotenuse for alpha. So sine is opposite over hypotenuse. So I'm going to use the sine is opposite over hypotenuse with the alpha. Sine of alpha, is the opposite over the hypotenuse. Opposite of alpha is A, the hypotenuse is C. So sine of 34 degrees would be A, which is 22.8, divided by C, which I don't know yet. That's the thing I'm trying to find. And in the same type of calculation, I multiply both sides by C and then divide by sine of 34 degrees, making sure that my calculator is in degree mode. I got about 40.77 for my C. So that's what I would do. And I would just write 40.77 in for C. And now I've solved the right triangle. So I have all three angles and all three sides. I found all the measurements of the angles and all the measurements of the sides. So I've solved the right triangle. Okay. The other way to find C is use the fact that A squared plus B squared is equal to C squared. Because we have a right triangle, we can use the Pythagorean theorem. And now that I know my A is 22.8, and I know my B, well, the rounded version of B was 33.80. I got 1662.28 is my C squared. And then hopefully we all know that to undo a square, we use the positive square root. We can use a positive square root here because it's a length of a side, so it's gonna be a positive number, right? Hypotenuse is gonna be positive. So square root both sides to get rid of the square. And in this case, it rounds again to 40.77. Okay. So that's an alternative way you could have found C. Are you okay with that? So once you find I, A, and B, you can find C using the Pythagorean theorem if you want. Okay. Or if you know an angle, you can just use that angle and SOHCAHTOA to find, you know, the angle on one side, then you can use SOHCAHTOA to find all the other sides. Now, I do want to point something out. Both of those numbers, both methods, I got 40.77 when I rounded to 2 decimal places. But I want to point out that if I rounded to 3 decimal places, I would have ended up with different numbers. I would have wound up with 40.773 when I use the sign with the sign of alpha on SOHCAHTOA. And when I used the Pythagorean theorem, I would have gotten 40.771. The discrepancy there is because that 33.80 is a rounded number. Okay. So it throws off this one by a little bit. So when I am solving, most times they come out the same, but there are certain cases where they may be off by like 100th or a couple of hundredths, okay? Or maybe even a 10th if we get into really big numbers. So the way the homework is set is it's set so that if you can get an answer one way and it's a slightly different answer another way, that both answers will work. All right, so that's what it's set up to do. So for instance, if I had asked to round answers to 3 decimal places and you put in 40.771 and your neighbor put in 40.773, they should have both been counted as right. Okay. Now, if you would have put in 80.3, obviously it's not going to be counted as right, but it set up so that it should count both as being right. Okay, whichever way you did it. As long as you did it correctly. So that's just a long version of saying sometimes because we're rounding these numbers, one path can lead to one thing and another path can lead to another. Any questions about that? It's pretty straightforward. Yes. So let's do another solving. In fact, Yeah, let's do another solving. This time, let's say, which two do I want? Gamma is always gonna be 90, right? I probably don't even need that one. Erase that. That's redundant. If I know, we have a right triangle. We have a right triangle. Let's say that I know beta is 28 degrees. And I know that my hypotenuse is length 9.35. I want you to try to find the alpha, the A, the B, and the C and the beta, but we already know the C and the beta, right? We can already fill these two in. I want you to try that on your own. Solve this right triangle on your own.
I think so. I got the angle and I was working on the length.
What? If you want to use 90,
No, okay.
no, you use
Alright,
So the gamma won't ever give you anything, because sine and cosine of 90 is
Okay,
1. And you don't ever use, in SOHCAHTOA, you never use the right angle. You always use the other two. One
Okay.
other. Is you. All right, let me do this. Okay. So I want you to, well, let's start out by finding the alpha. Okay, the alpha, everybody was getting really well at the 3 angles add to 180 degrees. So I take 180 minus 90 minus 28, and that gives me 62. All right. So alpha and beta, I always have to add up to 90. So that's a quick, hopefully, easy find. Okay. Now, I'm going to find A or B first. It doesn't matter. They're both equally easy or equally difficult to find. Okay. I'm going to use the SOHCAHTOA to find both. All right. That way I don't have to round anything. If I want to find, let's say the A, I just pick an angle to use. I can either pick the angle alpha or the angle beta. I used alpha last time, so I'm gonna use beta this time, okay? And I'm gonna notice that compared to angle beta, A is adjacent, right? And I know the hypotenuse. So I'm going to use cosine is equal to adjacent over hypotenuse with angle beta. So cosine of beta is adjacent over hypotenuse. And I'm using adjacent because the adjacent side to beta is side A. And you want to use the hypotenuse because I already know what C is. So I take cosine of 28 is equal to A, which I don't know, divided by C, which is 9.35. So all I have to do to find A is multiply both sides by 9.35. So 9.35 times the cosine of 28 is about 8.26. So then I can go back, fill that in. Now, if I wanted to, I could use the Pythagorean theorem, a squared plus b squared equals c squared, and then solve for b right here. But I think that I will use SOHCAHTOA again to find b. That way, I don't have to use this rounded number. Okay. And so, to find b, I'll once again use angle beta. For angle beta, b is the opposite side. And I was given the hypotenuse, so I'm going to use SOHCAH, the SO part, with beta, because I can say sine of beta is equal to the opposite over the hypotenuse. The opposite of beta is b, the hypotenuse is c. And now I'm using beta, which is a number that had not been rounded, and I'm using c, which is also a number that had not been rounded. So sine 28 degrees is equal to b, which I don't know yet, divided by c, which I know is 9.35. And so multiplying both sides by 9.35. Notice you always multiply by the denominator here, right, at that stage. And solve. So 9.35 times the sine of 28 degrees gives me a value of b, which is approximately 4.39. If you would have used the Pythagorean theorem, you know, you might have gotten 4.38 or 4.40 with the Pythagorean theorem. So there you go. Any questions about this? So if you're given alpha or beta and one of the sides, then you can exclusively use the SOHCAHTOA. That's in, yeah, alpha or beta with one of the sides. Then you can exclusively use SOHCAHTOA to find the other side lengths. And you can use the fact that the angles add up to 180 to find the measurements of the angles. We did one with one of the legs and an alpha. We did one with the hypotenuse C and beta here. Now there's only one other tricky combination. Okay. So if you're given an angle at the length of a side, we can do this. By the way, you're never going to be given just two angles because just two angles does not, the three angles don't determine a triangle because you can scale it up and scale. So you always have to have at least one side length given. However, There's another way to solve a right triangle. So we'll do another one. And that is, what if we have two sides of the right triangle? Now, it doesn't really matter which two sides you get. You can get the A and the C, or you can be given the B and the C, or you can be given the A and the B. Doesn't matter. Okay. Let's say we got the A and the C. Let's say that A is 67, whatever units we're talking about, and the C is 88 units. I want to solve this right triangle, find all the other measurements. Now, just like last time, there's kind of multiple avenues we can approach this with, right? Do I want to find my B first, or do I want to find one of my angles first, right? And it doesn't matter, you can do either way. Okay. A is 67, C is 88, M is 90 always. Why is that 180? Okay. I don't know. You guys have a preference or not a preference now? Let's find an angle first, okay? Angle first, okay. So let's find an angle first. I don't care whether I find angle alpha or angle beta. All right? Let's find angle alpha first. Okay. And it does not matter which one you pick. But once I say I want to find angle alpha, then I go to angle alpha and say, what are A and C? Well, A is the side opposite, and C is the hypotenuse, right? So the part of SOHCAHTOA which deals with opposite and hypotenuse is the sine. So we use sine because sine of alpha is equal to the opposite over the hypotenuse. And for alpha, A is the side opposite and C was the hypotenuse. And those are the two I was given. Right. Don't write this down. But if I were to try to find beta, what I would do is I would say, well, beta is up here, A is adjacent, C is the hypotenuse to beta. So I would have used cosine is adjacent over hypotenuse. Because compared to beta, the A and the C are the adjacent and the hypotenuse. Everybody get that? So I would have done that if I wanted to do it from beta. All right. I don't know what the alpha is, but I do know what the A and the C are. A is 67, C is 88. Now, at this point, we run into something we have not run into before. We know that the sine of alpha is a certain number, and we're trying to find what alpha is. Okay. There is a function on our calculator which is the inverse sine. We're going to learn more about inverse sine in later chapters. But for this section, it suffices to say that we can use the inverse sine to find alpha. And the way we do that is we say alpha is the inverse sine of 66 over 88. Just so we're all on the same page, our sine key is down here. To do the inverse sine, you just hit second and then the sine key. And then we go 67 over 88. And that means the angle alpha is 49.58 degrees. We'll round it to 2 decimal places too. So you guys got it? Inverse sine. So second and then the sine key. And by the way, if we were set up with a cosine, we can do an inverse cosine, just doing second cosine. And if we were set up with tangent, if we were given the A and the B, then we had to use TOA, the TOA part of SOHCAHTOA. Then we could have used inverse tangent to find the angle. So whichever one you're dealing with, if you're dealing with the SO, the KA, or the TOA part, right, of SOHCAHTOA, you can always find the angle using the inverse buttons. All right, and for right triangles, the inverse buttons will always give you what you're looking for. We'll have to, when we get into the inverse sine function later, we'll have to talk more about each one of those. But for right now, we have an inverse sine, an inverse cosine, inverse tangent when we need them for triangles. So the alpha is 49.58 degrees. Now, if you wanted to, you could do the same thing for beta with CAH, part of SOHCAHTOA, all right? But it's easier, once I get this, just to say angles are adding up to 180 degrees, so take 180 minus 90 minus 49.58, so 90 minus 49.58 is 40.42. Okay, to get the beta. And you will not have to put the degree label on there, that's already counted for you. Is that right? Now that we have our angle alpha and we have our angle beta, let's find B. And you can do this, again, you have multiple options now. You could use SOHCAHTOA with B and some other letter, B and A or B and C or with an angle. But I think since these are actually rounded numbers, Notice we had to round this angle, round this one. I think in order to find B, I'll just use the Pythagorean theorem. Is that okay? Because my A and my C had not been rounded. So I'll use Pythagorean theorem. In this case, you could have used SOHCAHTOA. That would have been fine too. If you want to use SOHCAHTOA with alpha or SOHCAHTOA with beta, that's fine. You might be just slightly off of what I'm at, but same thing. So A is 67. I don't know B. C is 88. Oh, shoot. 67 squared. 49. $77.44. B squared equals 3255. And then I'm going to take the square root of both sides. I got about 57.05 for my B. Is that what everybody else got? I try to use the rounded numbers as little as possible. Sometimes it's hard to avoid, sometimes it's not, but if you do use some of those rounded numbers, you can imagine this might turn out to be 55.06 or 55.04 or something like that. 57.06, 57.04, excuse me. Might be close, but get the point. Any questions about this process? Notice we also could have found the B first. It doesn't matter that you found the angle first or the B first. We didn't need the angle to find the B. We could have just used this. We found the B first, and then if you wanted to, you could have found beta by using the cosine as the adjacent over the hypotenuse. You're already given the A and C. But those are all of the solving of right triangles that we're going to do. You're either going to be given an angle and one of the three sides, or you're going to be given two of the sides. And if you know two of the sides, you can do this process. Don't forget that inverse function on your calculator. There's one for sine, there's one for cosine, there's one for tangent. All three of them will work fine. So if you're given two sides, you'll have to use inverse function on your calculator. If you're given an angle and one side, then you can use SOHCAHTOA and the fact, we're always using the fact that the angles add up to 180 degrees. But that's about it. That's about the whole thing. Solving right triangles. Any questions about solving right triangles? Well, this sets you up then to complete both those homeworks I mentioned earlier. The homework for 5.1 and 5.2, and the homework for 5.3 and 5.4. This was 5.4. Solving right triangles and SOHCAHTOA stuff that we did earlier. And so you have all the tools you need to complete those, and we'll start in on chapter 6 next class. Okay? All right. See you then.